Hi everyone, I am Pietro Liguori and I am a PhD student at University of Naples Federico II in Italy. This is a presentation for the International Workshop on Artificial Intelligence for IT Operations 2020, collocated with the International Conference on Service-Oriented Computing. This work introduces a runtime verification approach to detect the failures in the cloud computing infrastructures. These are the recent outages of three big cloud computing providers. These outages were caused by a bad software deployment and literally left the users in the dark without the possibility to use the services provided by the cloud computing systems. To support this consideration, there is a recent work analyzing several cloud computing services and showing that these services are often not able to reach the service level agreement. Cloud computing infrastructures are adopted in critical domains such as telecommunication or healthcare, and therefore they have strict availability requirements. These systems are very complex and non-deterministic as they are distributed systems. Any fault in the system related to the storage, network, software, and so on can cause a failure of the system itself. For example, data loss or unavailable resources. The complexity and non-determinism make difficult the quick detection of the failure, leading to a long mean time to repair and a poor quality of the services. Our case study is OpenStack, a free and open source software platform for cloud computing, mostly deployed as infrastructure as a service. It is the basis for many commercial products and it is used in several domains such as academic, industry, gaming, military, and so on. OpenStack is a very complex system and consists of several subsystems. For example, Nova is used for virtual machines, Cinder for the volumes, and Neutron for the virtual networks. Let's suppose that a user wants to create an instance by using the API provided by the Nova subsystem. This request starts an exchange of events among the OpenStack subsystems. This workflow is just a simplification of what really happens in OpenStack. A bug in the system can cause silent or undetected failures. These failures occur as omissions, delays, or out-of-order events in these workflows. The work introduces an approach for runtime detection of failures in cloud computing systems. It uses a form of tracing that is called black box because it requires no knowledge about the internals of the systems. Also, it uses a stream-based runtime verification technique to model the relations between streams of events observed during the execution of the target system. All this allowed us to create lightweight monitoring rules. We investigated the feasibility of our approach in the OpenStack, showing that the approach can be easily applied in the context of an off-the-shelf distributed system. To preliminarily evaluate the approach, we executed a campaign of fault injection experiments by literally injecting a software fault in the system and by applying an intensive workload that stresses the three most important OpenStack subsystems, Nova, Cinder, and Neutron. The concept of invariance is important in order to define relations between events. They are indeed the properties that hold over events during the execution of the system itself. For example, the operation buy performed by the clients can follow only the available status from the server. This is an invariant. In complex and distributed systems, it is very difficult to discern the requests of multiple users and to properly keep the happened before relations between events. This indeed would require a vector clock and a session ID. However, these mechanisms are not supported by common trace infrastructures, and therefore they require an effort of manual annotation of the code, leading to an impact of the overhead. We instrument the system under test to collect the events changed in the system during the experiments. To instrument the system, we do not require any knowledge about the internals of the system under test, but only basic information about the communication APIs being used. This approach is especially suitable when testers may not have a full and detailed understanding of the entire cloud platform. Let's suppose that two different users perform the same request by using the Nova APIs. Every request creates a workflow consisting of an event type A followed by an event type B. Our formal tracing just collects all the events changed in the system without discriminating the events generated by different users or sessions. An invariant, in this case, can be expressed by the following one. A specific number of events of type A is eventually followed by the same number of events of type B. It is not always possible to model the properties with the happened before relations between the events. For example, let's suppose that event A from nova to neutron is followed by an undefined number of events C from neutron to nova. This is a quite common situation. Indeed, the network operations are performed by the neutron subsystem in an asynchronous way. This behavior leads to a more non-deterministic variations of the events in the traces. Given the high source of non-determinism affecting the network operations, it is not possible to create rules based on event ordering. In these cases, we define the monitoring rules related to the network operations by checking, at runtime, if a specific event type occurred in a number higher than a threshold. The question is, how do we define the thresholds or the relations between the events? Well, after the instrumentation step, we collected the correct execution of the system, step number 2. To define its normal or correct behavior, we exercise the system in fault-free conditions, that is to say, without injecting any fault. Moreover, to take into account the variability of the system, we repeat several times the execution of the system itself, collecting different fault-free traces, one per each execution. Then, we analyzed the collected fault-free traces to extract the relations on the order and on the occurrences of the events. Therefore, we defined a set of failure monitoring rules. This is the step number 3. We are currently working on an algorithm using invariant analysis in order to automatically identify patterns. Finally, we synthesized a monitor from failure monitoring rules expressed according to a specification language. Step 4. The monitor takes as inputs the events related to the system under execution, and it checks at runtime whether the system behavior follows the desired behavior specified in the monitoring rules. Step 5. Any runtime violation of the defined rules alerts the system operator of the detection of a failure. We defined happened before relations between the events for the operations related to the volumes and instances. In particular, we derived 3 different rules for the attach volume operation. The rule number 1 states that the event compute research block device name is eventually followed by the event compute attach volume. The evaluation is performed in terms of failure detection coverage, defined as the number of experiments identified as failed over the total number of experiments that experienced a failure. By using these 3 simple rules, we were able to identify the 90% of experiments that experienced a failure on the operation of the volume attachment. Based on the fault-free observation, we defined the monitoring rules related to the network operations by checking at runtime if a specific event type occurred in a number higher than a threshold. Thus, for each event type, we defined a threshold as the higher number of times that the event type occurred during the fault-free executions. In the case that the number of observations of the event type C is higher than the threshold, then a failure detection message alerts the system operator of the detection of a failure. We derived 3 rules and we applied these rules on the experiments that experienced a failure on the SSH connection to an instance. The 3 rules were able to identify the 38.46% of the SSH failures. We compared the coverage provided by our runtime verification approach with the coverage provided by OpenStack API errors by design. API errors notified users that the system is not able to perform a request, thus they work as a failure detection mechanism. The table shows the failure detection coverage of both approaches, considering different failure cases that are related to different operations. The results show that our approach is able to identify a failure in the 79.38% of the failures, showing a significant better performance of the OpenStack failure coverage mechanism. In particular, the table highlights how our rules are able to identify failures that were never notified by the system, for example, the instance creation and the SSH connection. The runtime verification approach shows lower performance only in the volume creation case failure. This suggests that the need to add further monitoring rules or to improve the existing ones for this specific case. We evaluated our approach also in a simulated multi-user scenario. To simulate concurrent requests, 10 traces, 5 fault-free and 5 faulty, are mixed together by alternating the events of all the traces but without changing the relative order of the events within every single trace. The faulty traces are related to the same failure type, for example, volume creation. And for each failure type, we performed the analysis 30 times by randomly choosing both the faulty-free and the faulty traces. The table shows the average failure detection coverage and the standard deviation of our monitoring rules for all the failure volume cases. The preliminary results can be considered promising. However, the high standard deviation indicates that the average failure detection coverage is very sensitive to the randomity of the analyzed trace. This work proposes an approach to runtime verification via stream processing in cloud computing infrastructures. We applied the proposed approach in the context of the OpenStack cloud computing platform, showing the feasibility of the approach in a large and complex off-the-shelf distributed system. We performed a preliminary evaluation of the approach in the context of the fault injection experiments. The approach shows promising results both in single-user and simulated multi-user cases. Future work includes the development of algorithms able to automatically identify patterns using statistical analysis techniques such as invariant analysis. We also aim to conduct fault injection campaigns by using a multi-tenant workload in order to perform an evaluation in a real multi-user scenario and to analyze the overhead introduced by the approach. This is the conclusion of the presentation. Thank you all for your attention.